It is my pleasure to introduce our speaker for today, Dr. Linda Tacconi. Dr. Tacconi is a group leader and a deputy to the director at the Infrared and Submillimeter Group of the Max Planck Institute for Extraterrestrial Physics in Garching, Germany. To my knowledge, she is giving the first and only intercontinental talk of this series, and she's speaking to us directly from Europe. Among other accolades, Dr. Tacconi is a Saclay lecturer and a recipient of the Lancelot Berkeley American Astronomical Society Prize, which is awarded for highly meritorious work in advancing the science of astronomy. Dr. Tacconi has done a range of groundbreaking work on gas properties of galaxies, spanning from local dwarf galaxies, where I first met her in the literature, to high redshift submillimeter galaxies. In recent years, she has focused on main sequence galaxies, that is to say, normal galaxies at their redshift. And these galaxies, she has been focusing on normal galaxies during the cosmic noon period, which is a period of peak star formation activity of the universe. And about this, she has written some of the most well-cited and influential papers. So without further introduction, I now turn the control to Dr. Tacconi.
Thank you very much, Alberto. Thank you very much. And thank you for inviting me to give one of these talks. I feel very privileged being one of the few speakers coming in from Europe. So good evening from Europe. Good afternoon to the rest of you. What I'd like to spend the next 25 minutes or so telling you about is where we are in our understanding of galaxy evolution through the numerous studies that are now available in the literature of the cold gas, the gas from which the stars are formed. And most of what I'm going to be talking about has been summarized in an annual reviews article that is just about to come out, that was written by my colleagues Reinhard Genzel, Amiel Sternberg, and myself. I would also like to acknowledge the various teams whose work has gone into a lot of what I'm going to talk about, and that is our FIBS CO team, the ex-cold gas team that's done CO work at low redshift, and the Herschel PEP team that has done a lot of work with in the far infrared dust continuum with Herschel. So let me get started. So what I want to do in this talk is a little bit different, I think, than what a lot of people have done in talking about cold gases. I really want to put it in the context of how galaxies form and evolve. And so we know in this very famous plot that the star formation rate at the time of about 10 billion years ago at redshift 2 was on the order of 10 to 20 times what is seen today, the star formation rate density in this very famous plot. We also know that the bulk of star formation is formed, and as Alberto has said, in galaxies which lie on the so-called main sequence, which is a tight relation between star formation rate and stellar mass. And it seems to hold at most redshifts, at least as far out as we've been able to determine, well beyond redshift 3 by this point. This is just a sequence of the work summarized by Renzini and Peng, which shows the main sequence in red here at redshift 0, redshift 0.5, redshift 1, and redshift 2. And the more quiescent elliptical type galaxies lie down here. So at redshift 0, just for your information, the Milky Way is sort of an average, very massive main sequence galaxy. So we know that, and we also know that about 90% of star formation forms in galaxies that lie along this relation. Now this relation is more or less has the same form at all redshifts. The only difference you can see in this plot here is that there's an increase in star formation rate, but the shape of the main sequence is the same. So we want to understand what's causing that. And of course, the takeaway is the cold gas is playing a massive role there. Another thing we know is that galaxies, when they hit a mass of about 10 to the 11th solar mass, which is sometimes called the Schechter mass, somehow turn off their star formation. And we want to understand what happens there. So in the past, a lot of people thought that the whole process was driven by massive major mergers. And now, going back to actually a paradigm that was very popular in the mid-70s by Martin Rees and Simon White, we're back to thinking that galaxies form in a more gentle way, in a more equilibrium way, with an interplay between a very rapid accretion from the halos of galaxies, which is a very strong function of redshift, together with it's a balance between the accretion and then what's used up in the galaxy in star formation rate, which is this term here, star formation rate, where some fraction of that gas then is given back after the massive stars evolve and die. And then, the massive stars evolve and die here, and minus a fraction that's locked up into low mass stars. So it's this balance between inflow, outflow, star formation that determines the reservoir, as you will, if you will, which is what's available to form stars. So that's sort of the kinds of those terms we want to understand what each of those terms are, and how that affects the evolution of a galaxy. So you need to know things like the stellar mass, the molecular gas mass or gas fractions, something called the gas depletion time, which is how fast are you using up your molecular gas, obviously the star formation rate, and then a better way to even characterize that is star formation rate per stellar mass, a normalized star formation rate, which is sometimes called specific star formation rate. The inflow rate, of course, which you get mostly from simulations, and what fraction then is due to merger type perturbations. So you can see that most of those terms involve molecular gas in some way or another, and that's what the rest of this talk is going to deal with. So there are basically three methods that we know to get it, or now actually four, as I'll touch on at the very end of this talk. But the three main methods up till now have been to use CO line emission. I think Christine Wilson, when she gave her talk, already told you that you can't observe the largest constituent of the molecular gas, which is molecular hydrogen. We cannot observe that directly. So we need a tracer, and traditionally that has been CO. Now, that the pluses of that is it's pretty well calibrated in regions of the Milky Way, and Alberto Bellato has written, I think, this seminal review article on this topic, and you should all definitely go read that. But we know the conversion factor in the Milky Way pretty well. But we also know that in other galaxies, it is strongly dependent on galaxy metallicity, such that low mass, low metallicity galaxies seem to have much different conversion factors than, the Milky Way one. We also know that it's a function of density and temperature of the gas, but to a lesser extent. So we have created, there is by now very good corrections, very good understanding of how the conversion factor varies as a function of these various parameters. The other thing that is very good about CO is that because of the CO ladder, this is taken from a paper of Chris Carilli and Fabian Walter, we always have a CO line that we can observe. But then you have to make a correction down to the j=1 to 0 line on which the conversion factor has been calibrated in the Milky Way. And so you need a correction for the excitation of the gas there. But that's I think, a fairly minor correction factor. The other two methods involve observing the dust continuum. And one method has been to use multi-band observations from Herschel, the Herschel Space Telescope, which unfortunately is no longer operational. And then you do modified black body fitting to get dust mass, and using a dust to gas ratio, you can convert that to a gas mass. Recently with ALMA, because this end of the spectral energy distribution is optically thin, this Rayleigh-Jeans tail, so-called Rayleigh-Jeans tail, you can, with one continuum measurement in the millimeter, submillimeter, get a gas mass directly from a dust mass, again applying a gas to dust ratio. Now, metallicity haunts us in all these three methods, because when you don't have metals, you have a highly varying conversion factor for CO, and you have a probably varying gas to dust ratio for the two dust methods. So metallicity means that we have a very difficult time to get direct molecular gas masses at low masses, at low mass galaxies. And that mass shifts to higher and higher masses as you go higher and higher redshift, because galaxies don't have as much metals in them at high redshift. But by now, what we've been able to do, my colleagues and I have been able to assemble samples of well over 2,000 galaxies using all three methods, and we can cross-calibrate them to determine relations that will help us understand galaxy evolution. So this is just a compendium of the 2,000 galaxies or so that we have incorporated in our study. And this is by no means complete, and it's by no means up to date. This is already out of date a year after we finished the article. But we have a postdoc who's now working on the next version of this, who will probably double the number of galaxies that we have so far. So in the early times when we were doing this, we were definitely dominated by CO and Herschel measurements, but that's changing now, and there's ever more ALMA single band measurements coming into play. So for the rest of the talk, I'm going to talk to you about just the kinds of relations which are important, which I already mentioned in the beginning of the talk. That is depletion time, which is just think of it as the mass of molecular gas divided by the star formation rate. It just gives you the rate at which a galaxy is using up its reservoir. It's a lower limit to the real depletion time, because of course it does not take into account any gas that's put back into the interstellar medium from evolving stars. So what I've shown here in this plot is for those galaxies now that are on the main sequence, we want to determine the relation between depletion time and redshift. So the trend of depletion time with redshift. And what you see here on the y-axis is the depletion time, and on the x-axis, log of 1 plus redshift. And the different color points are the depletion times and the gas masses that are determined by the three different methods. Green are the CO points, which are dominant. The dominant method is the lowest redshifts. The open black are the ALMA 1 millimeter or 0.8 millimeter dust measurements, and red are the Herschel measurements for the SED fitting. Now, the first thing you can see is that these three methods agree very well. There is no obvious discrepancy in the gas masses that you get using one method or another method. So that's very good news, because we've been able to what we've done here is taken all three methods to this sample of galaxies, applied consistent cross calibrations for star formation rates, for stellar masses, and all the other parameters, And we can derive those relations. And you can see that all three methods give you a fairly consistent answer. Now, the ALMA points are mostly at high redshift. The CO points tend to be at low and intermediate redshift, and Herschel as well. So that there is some differences in the redshift coverage. But so we've been able to determine a redshift distribution where we see that the depletion time is a slowly varying function of redshift with a slope of about -1. What that means is that at this peak of cosmic star formation, or cosmic noon, as it's called, there has been basically a factor of 3 decrease in the depletion time, or if you look at it the other way, or an increase in the star formation efficiency from redshift 0 to 2. Now, remember I told you that there was almost a factor of 20 increase in the star formation. So just this increase in efficiency or decrease in depletion time does not account for that. So you know that there's got to be something else. Now, once you take out the redshift dependence, you can look at other dependencies in depletion time. And here, the next thing you want to do is look at things that are in the normal regime and also in the starburst regime to see if you see a difference in how galaxies convert their gas into stars as you go into this starburst mode or going off above the main sequence. So what's plotted here is the depletion time, or delta depletion time, as relative to the main sequence as a function of main sequence offset. So here, the starburst down here, and this is the main sequence trend line right here. And these are things that are below main sequence. So what you can see is that, again, there is a definite trend that as you go into the starburst regime, you have a much faster, shorter depletion time. So stars are forming more rapidly, more efficiently as you go into the starburst mode. If you then fit out that as well, you can look at residuals of other things. These measurements are all global measurements. We do not have spatially resolved information. So what you can see here is that now if you plot the depletion time residuals as a function of stellar mass, basically there's almost no dependence on stellar mass. Now this is a very important point because remember I told you that it's really difficult to measure the gas masses in low mass galaxies. Now we have a few cases, especially at low redshift, where the X-cold gas work that's been led by Amélie Santonge, there's quite a few, she does have some lower mass galaxies. Now, basically what you can see is that there's no dependence on mass. So you can push down into a regime that you actually can't observe just by following the scaling relations in redshift and main sequence offset. So that's pretty important because that allows you to calculate the evolution of gas mass for galaxies that you can't really see. So the takeaway point there was the depletion time varies only with redshift and with main sequence offset. Now, the other set of relations that we want to look at are those of gas fraction. Now you do the same thing in these series of 4 plots here. We've plotted in this panel here, I'll just focus on this one onto the left, the gas to stellar mass ratio, or so it's like a gas fraction as a function of redshift. And here what you can see is that there's a very steep increase with redshift up to about a redshift of 2. And that seems to go almost exactly as the accretion rate, so 1 to the 2.5 power or so. That's very interesting. So that says that galaxies at higher redshifts, especially up to redshift 2, maybe even 3, have much higher gas fractions, much more molecular gas than galaxies at the Milky Way epoch at redshift 0. Here's just another way to plot it on the lower right here of a sort of a baryonic fraction of molecular gas over the sum of gas plus stars, which shows basically the same turnover trend. Now, if you fit out this redshift, this distribution, this dependency, you then can also look at the differences with main sequence offset. And here you see almost the mirror, not surprisingly, of what you saw with the depletion time, where the gas fraction above the main sequence goes up, almost with the same inverse slope. So the slope of 0.5 is a minus 0.5. And it's a fairly strong function as you go from on the main sequence here at 0 to above the main sequence into the starburst regime. So galaxies above the main sequence also have increased gas fractions as well as shorter gas depletion times. Then when you fit that out and you look at the stellar mass dependency, here you see a strong, there is a trend where the more massive a galaxy is, the lower the molecular gas fraction. And in fact, it drops quite dramatically at this redshift of 10 to the 11th, right around the Schechter mass. So this is another signal that galaxies are quenching because they're somehow running out of gas at that stellar mass. So the takeaway point here is that the gas fraction varies with redshift, main sequence offset, and also stellar mass. So now we want to put this all together back into the evolutionary picture that I started with. So if you look in this upper right panel here, let me just zoom in on that a little bit. Oops. What's shown here is the gas density in solar masses per cubic megaparsec as a function of redshift. And so lots of people have been spending a lot of effort now in doing different kinds of studies with studying deep fields to get at the gas evolution by going in an unbiased way and integrating on patches of the sky. Now, one of the ALMA large programs, aspects, is shown here in green at the different redshift bins here. There's another survey in Hubble Deep Field North, which was a precursor to aspects. Then the JVLA, in a project led by Dominic Riechers, did a study called Cold Z, which looks at the lowest J lines, and has been able to go out to higher redshift. And this is so the boxes, the orange boxes, show the results from that survey. One of the PhD students, Laura Lenkic, took all of our FIBS data and ignored the fact that we pointed at a particular source, but looked for serendipitous sources in all of the data that we had amassed, because it's actually like a giant deep field in a way. And that's what's shown here in these gray boxes. So you can see the gas density evolution from all these surveys shows a peak at around redshift 2 and then a decrease at higher redshifts. Now remember what I told you, that with our depletion time scaling, we can actually do the same thing with our pointed surveys, because we are only dependent, and it's because we care mostly about the main sequence galaxies, because 90% of the stars are formed that way, and the only other dependency is with redshift. We can then take the Maddow relation on star formation, multiply it by the depletion time, and get our own gas density. And that's what's shown in this blue curve here. And you can see that whether you use the pointed method and work backwards to the using the star formation relations, or if you use a deep field approach, we're pretty much getting the same answer. And that's also very reassuring and very good news. So how does this all fit into our picture of evolution of galaxies? So on the left plot here is, again, the Maddow, the Maddow-Dickinson plot of the star formation density here. In cyan is, if you use an equilibrium model if you apply this so-called equilibrium or bathtub model with parameters that we know for the outflow and the inflow, you get this, or typical parameters for the outflow and what we think we know from the inflow, you get this cyan curve here. You see it agrees pretty well with the Maddow and Dickinson relation. Now, this curve here for the molecular gas is plotted on the right-hand side. And what that shows is that we have this initial growth of both gas accretion and the molecular reservoir is increasing up to about a redshift of about 2. And in fact, the growth of the reservoir the reservoir keeps growing until you get, this is a plot here of growth rate, until about redshift 2.5. But actually the maximum of the gas density actually happens a little bit later than that, probably because we're already starting to get even more gas from basically from stars that are ejecting material back into the ISM. Here's in green, just showing the curve for the H1 as comparison. Most of this has been done through absorption line studies at high redshift and through H1 studies of galaxies themselves at low redshift. So you can see that the H1 and the H2 look very different in their evolution, although the H1 dominates at all redshifts, but it doesn't seem to vary. It doesn't seem to vary the way the molecular gas does. And the molecular gas is the stuff that we think is causing this change in the star formation rate density as well. So you can see this all sort of hangs together. So what are the big questions right now? Well, we need to probe to lower masses, and I mean, although we think we're pretty sure we can use our scaling relations, it would be good to have a few more points at low mass, but that's going to be hard to do because really everything is affected by the metallicity that is low at higher redshift. So one place where we still need a lot of data is at higher redshifts, and here is where ALMA is starting to come into play, because you can use not only CO, but you can now observe ionized carbon, C+. And there are various ways where people are trying to then go from C+ to get to a molecular gas mass. There's still quite a bit of work to do there to get those calibrations down, but I think that's going to be the next frontier, one of the next frontiers. So I think we understand, I hope what I've been able to tell you is the picture we have, at least up to redshift 2.5, is pretty consistent with this main sequence equilibrium growth of galaxy evolution through accretion and through a regulation of the molecular gas reservoir. So the next 2 points, the next 2 places where I think we're going to go is, on the one hand, higher redshift, which I'll talk about in a minute, but a really important thing that we need to understand then is how stars are actually forming in environments where half of the mass is in molecular gas. And so we need to go to subgalactic scales. And I think the NGVLA is going to be really critical for this, because you'll be able to observe the low J transitions with super resolving power and super collecting area. tried to do this already, both with ALMA and with the NOEMA array in the northern hemisphere. And this is a map of one of our sources with NOEMA, where you can see this is a 0.3 arcsecond resolution map of the CO4 to 3 line in red, superposed on an HST multicolor image. And you can start to see lots of structure in the molecular gas. And if you look at the channel maps, you can see here in color, these are the individual, molecular complexes, still at several kiloparsec scale, but there's an awful lot of structure. And because with the CO line, we also get exquisite information on kinematics, we can derive CO rotation curves that push way out into the disk. We can look for non-circular motions to see the buildup of bulges. This is very time-consuming with all of the current telescopes, including ALMA, and it will be as well with the NGVLA, but it's going to be absolutely critical to get down to scales of, a kiloparsec or so in enough galaxies at different redshifts to understand how, in a very gas-rich environment, stars are forming and how bulges are forming in the centers of galaxies and how galaxies are evolving that way on local scales as well. The next frontier is obviously pushing to the highest redshifts. And I've already said, I think here the C+ line is already proving to be an amazing resource. So you can use the ionized carbon line at 158 microns with ALMA, which is redshifted into ALMA band. And here's a recent Nature paper by Neeleman et al., which shows a beautiful C+ rotation curve at a redshift of 4.5. And so you'll be able to do great kinematics as well with the C+ line. But then you can push out to the highest redshifts where it's very difficult to get a moderately excited CO line in the bands we currently have. So this paper from this Alpine survey, which was another one of the ALMA large programs, shows their targets in red here, where they've been able to make detections of C+. And you want to be able to calibrate that and get back to a molecular gas mass. So those are two areas where I think a combination of the NGVLA with ALMA is going to be a very, and then NOEMA in the northern hemisphere, a very important path forward in those areas. So with that, I would like to just put up my summary and just take questions.
Okay, thank you, Linda. Thank you for a great talk. So we already have several questions here, and I'm just going to try to go through them more or less in order. So you were talking a lot about one of the very important things here, which is the mass of gas. But can you elaborate a little bit on how you measure the star formation rate? And of course, one of the possible concerns is, are there correlations between the determination of star formation rate and the determination of gas mass? Okay,
so in the galaxies where we have observed or used in our sample, we have tried as best as we can to always use star formation rates that are determined from multi-band data, including points from Herschel, but at least from Spitzer. If we can, so use the so-called ultraviolet plus infrared method to get the obscured as well as the unobscured star formation. That isn't always possible, and so you often have to do SED fits to get the star formation rates as well. Or in some cases, we can use H alpha with some kind of an extinction correction, but that's always, that's tricky. The star formation rate in sort of a, it's kind of almost sinister, that where we can get very good star formation rates is in unextincted regions or low mass galaxies. It's much easier than in the more obscure dusty galaxies, where we can get very good gas masses, but it's much harder to then get the star formation rates. So But I hope I've answered the question. I think it's, we are trying to account for all of the star formation that we can, and that's using as many the ultraviolet plus the infrared in calculating the star formation rate.
Thank you. So next we have a two-part question here. So do gas-rich galaxies with a poor star formation rate exist?
We've all been trying to look for those. I started trying to look for those back in 1987, and I think I never found one. There are, in the deep field studies, there are quite a few detections that don't have obvious counterparts. Now, it's possible that those are some kind of source like that, where the star formation is so obscure that we're not seeing it at all. But whether there are just cold galaxies sitting there with lots of gas and not doing anything, I don't think we've ever seen anything like that, because as soon as you get a lot of gas, a lot of dense gas, it collapses and you get some stars. And so that will sneak out in some way, or it will make itself known in some way or another, even in, you know, a super obscure galaxy like ARP 220. We still know that there's lots of ongoing star formation.
So the second part of this question is, do you, and you were answering a little bit of that already.
Okay.
Do you think there is a particular type of observation or a particular survey design that will allow you to identify these, you know, very gas-rich, very star formation poor galaxies?
Well, it gets very expensive, so it would be good to at least know whether or not there was one. But I would have thought that trying to follow up some of these unidentified sources in either aspects or in the, you know, the sources that Laura Lenkich has found in our FIBS data, without obvious counterparts. I think trying to really pin down what those are, whether they're real, go back and look at them again to make sure that they're real, first of all, and then do follow-up work. I think before we go and plan a huge survey, I think we need to make sure that we can find one. We already have enormous amounts of data. Actually, there was there's another really great ongoing project that's led by one of the team members is Anna Klitsch. What they're doing is taking ALMA calibration data and stacking it and looking for high redshift galaxies that way. So I think we have a lot of data where you could go and mine already to see whether these things are there. And then once you can verify that they're there, then we plan the next survey.
Great. Okay, so the next question has to do with morphology. So do you have morphological type information for these high redshift galaxies? And for example, when you talk about the massive galaxies that have a, relatively speaking, a lack of gas, is it because they are sort of ellipticals, or is it because, you know, they look like normal spirals, but they just have less gas?
We do have quite a bit of morphological information because of these surveys were not done in a vacuum. We have huge ongoing programs at the Very Large Telescope at ESO, both with adaptive optics and without adaptive optics. And also, we have always targeted those fields that HST has targeted in their legacy surveys. So the CANDLES fields or the AEGIS fields in the north. And then the same goes for the ALMA surveys in the south. They're always targeting things that HST has already done a lot of the optical work. So you can get very good axis ratios, morphologies, light profiles already for most of these galaxies. Of course, not for the Herschel stacks, the things where we've already used stacks of galaxies, that's obviously not, but for the individual sources, yeah, for most of them, we do know what their morphologies are, and some of them have, you know, very massive central components, bulges, look like they may already be on their way to transforming into elliptical-like galaxies, or S-zeros, or things like that.
Good. Okay, so when you have been talking about depletion times for the gas, but of course that depletion time doesn't take into account galaxy outflows in the definition. So how important is gas outflows from galaxies in the real depletion time?
Yeah.
How important are they in particular for low mass galaxies, if you can say a few words?
Yeah, for low mass galaxies, it's really important because we know that it doesn't take much to get to put from star formation to eject gas at least into the circumgalactic medium. So it is very important at low mass galaxies. The theoretical simulations also show that stellar feedback is incredibly important at low mass. At high mass, we know that AGN feedback is very important. So the feedback due to the black hole sort of pushing large amounts of gas at very high velocity out into the CGM or even beyond. And that's one of the things we think is leading to the quenching of the most massive galaxies. So feedback is probably extremely important at both ends and at all masses. It's just which type of feedback which type of outflow is driving is important. At lower mass, it tends to be more the star formation feedback. At higher masses, it tends to be more the black hole driven or AGN driven feedback. But it's very hard to quantify that and to add that term into depletion time, which is why everyone is just using the most basic formula of the depletion time.
Great, thank you. Okay, so this is an important question to think about, but have you thought about, or can you please elaborate a bit more on the influence of the choice of different IMFs on the results?
We have always chosen the Chabrier IMF. Early on, we had played around a little bit when we were studying submillimeter galaxies with top heavy and bottom heavy IMFs and try to make sense about it. But to be honest, it seems to be, no matter where you look, the IMF doesn't seem to vary that much. I don't think we have evidence that's the thing that's varying most. So the best we could do is just adopt one and stick with it, and that's what we've tried to do. But yeah, that's.
Yeah, this is a $10,000 question.
Really, I'm looking at some of my colleagues who are on the screen here who also will have the same problem on all of their work.
So you were talking about infrared data, but can you think of current facilities like SOFIA, for example, providing some of the infrared data that you need?
I think it's really hard for SOFIA to hit the higher redshift targets. Certainly it can do a lot at lower redshift. And there may be bits of parameter space because that Herschel did not hit. But I think beyond a redshift of, 0.5, I don't think you're going to get, it will be very hard to do it with SOFIA. You'd need a much bigger telescope.
Okay, so we have a couple of questions that are related, so I'm going to try to mix both of them. But can you tell us a little bit more about the uncertainties that enter into the determination of the cold gas mass at higher redshift, and particularly, what may be happening with the CO dark gas?
Yeah, CO dark gas. That of course is the big issue at low mass. It would be great to be able to somehow have, say, C+ and CO in a consistent set of galaxies. to be able to determine through some then inference from the ionized carbon as to how much of the H2 is not being traced by CO. But that is a really hard project, actually, because it's really, if you stick to Redshift 2, you're talking about very expensive ALMA band 9 observations to get the C+, and you'll get the CO reasonably okay. And you could do a cross correlation by also getting the dust continuum. But as you go to higher Redshift, this is going to be, then the C+ becomes easier, but then the CO becomes so hard. So it's actually a really challenging project. It will take a lot of telescope time, but it would be great. It would be great to come up with a sample where we had high redshift sources with both CO and C+. Now, actually, the Alpine team, I believe, is following up with CO observations at the JVLA. And so that is really an important project at the higher redshift. But for Redshift 2, it's actually even hard. It's harder to do it at Redshift 2 than it is probably at Redshift 4.
Great. Okay, so I have a person asking about something that is very interesting. I don't know if you have thought about, but does any of these data provide some hints or some information about how globular clusters end up forming?
That would be a great thing to, this is where we need the spatial resolution. But, even with ALMA, it's really hard to get the spatial resolution in a non-gravitationally lensed galaxy. So probably the way to do it is to find a few gravitational lenses, which people are doing, and go to as higher spatial resolution as you can, because you need a few hundred parsec scale resolution to then be able to map out both the dynamics of what's happening on those scales and also look for these dense pockets of gas. But so far that, we have not in our samples been able to get to those spatial resolutions.
Okay, so I'm going to paraphrase Bill, the last question that I have here in the list, which I think has to do with the information that comes to us from the gas Madao plot, essentially. So when you look at the behavior of the density or the derivative of the density, what are the parameters that helps you constrain? So what physical parameters does that give you information on?
I guess I don't really understand the question. So we have a well-defined star formation evolution plot, and we have we've tried to suss out the parameters that are important for the gas. And we found that for the depletion time, the main parameter is only the redshift. And since at least for the main sequence population, we have just a strong trend with redshift. And you can then just take that and go back using the star formation rate density plot. You just have to multiply it by the scaling, and then you get exactly what you need on the gas parameters. Is that what the question is, or?
Not entirely sure, because the question is about Z max for rho and d rho dt. So I may not be interpreting correctly what the question is.
So we also use just parameters on the outflows, both from simulations and also just from our own work on star formation outflows to get things like mass loading factors to find out what the outflow parameter is. And so you just solve that equation, more or less, the equilibrium equation. if that's the question.
I think that was the.
And you'll get the maximum. You'll see what the maximum redshift comes out. I mean, that it does give you the maximum redshift.
Okay. Good. Well, I mean, we are going to close here. So I'd like to thank you again for a great talk and illustrating what the future of the field looks like and what the present of the field is like. Oh, thank you, Linda.
Thank you. Thank you very much again.